and I'll be presenting in this short video the basics of finite element analysis. I'd like to start with some prerequisites just to talk to us about some of the things we're supposed to know before we can learn finite element analysis. First, we are supposed to know our basic algebra. That's simply how to simplify algebraic expressions and how to solve simultaneous equations. Then apart from that, you need to be familiar with your matrix operation, just primarily addition and subtraction of matrix, multiplication of matrix, how to look for determinants and also inverse of matrices. Then integration, you ought to be familiar with your basic integrals. That's how to integrate some simple expressions like x squared, x cubed, x raised to the power n. Case scenario you would encounter is integration by parts. Then after that, you ought to be familiar with differential equations and the related terms such as ODE, simply ordinary differential equations, PDE, partial differential equations, initial value problems, that's IVP, BVP, boundary value problems, and the order of an equation. Once you're familiar with all these basic mathematics, you are good to go. Then what is finite element method? Finite element method is a numerical method used to obtain an approximate solution to differential equations by discretizing the entire problem domain into small, fine shapes that we call elements. And usually this element can be represented by simple algebraic equations. There are some terms we can see here that are italicized, they are bold, and they are in blue fonts. First, numerical method, we are familiar with that. These are techniques that are used to get approximate solution to differential equations when you cannot solve them analytically. Then to discretize is to break down a domain into small pieces. I will explain this using a building. Of course, we know a building is made up of several blocks that are mounted on top of one another. If we take away the paintings, if we take away the plasters, we see the building in its form, its original form, made up of several blocks. So if you pick a structure, you want to analyze it, and you divide it into several smaller blocks, that's what you're doing, is discretizing. You are discretizing the domain. Then the problem domain could be anything. It could be the building, the structure that we just talked about. It could be, say, flow through pipe. It could be anything. Then those small shapes that you break it into, that forms the building blocks, is what we call elements. This method is widely used in solving engineering problems that are governed by complex differential equations. That's when you have engineering problem and there is a standard differential equation that you can use to describe everything that is taking place in that form of problem. We can apply finite element method in such situation, and this situation ranges from heat transfer. Of course, there's a governing equation for heat transfer, to elasticity, whether it's bending, whether it's equilibrium problem, whether it's dynamic structural analysis. All these have equations that are used to take care of them. The beam bending, which is also a form of elastic problem. Then we have flow through pipes, flow through even diffusion, flow through solids. Then we have magnetism, which involves the flow of electric and magnetic fluxes. Even electricity, they can use this method to analyze certain situations in electricity as well. Then we have energy. These are some practical example governing equations and problem description. Then you have heat transfer, and heat is being moved from one point to the other via any of the heat transfer mode, whether it's conduction, convection, or radiation. There's one standard governing equation which we can see here that can be used to describe this situation. Then this is the beam bending equation, when a beam is subjected to several loads, or whether it's dynamic or static. This equation is suitable for solving it, and you can choose to solve this equation using the finite element method. Next, we'll move on to the procedure for finite element method. What and what we won't do if you want to undertake finite element book question in your exam. But you must understand that some of these steps we'll talk about, you can do them analytically, but it could be very tedious. But more realistically, these things are done using a computer. So a computer basically does all these things for you. And there are standard finite element software that have all these things embedded in them as built-in algorithms to undertake finite element analysis for different forms of problem. There are several of such software. We have ANSYS, is a very popular one. We have Abacus, we have Nastran, we have Console Multiphysics. Basically, you are likely to undertake all of the following. The first thing to do is to understand the mathematical equations, what you call governing equations for the problem that is being idealized. So, and that process is called mathematical modeling. Then after that, you need what they call a geometrical representation of the problem. If it's a flow through a pipe, we know that the fluid that is flowing through the pipe would take the shape of the pipe itself. So if you want to produce a geometrical model, you're going to just draw the shape of the pipe, the internal shape of the pipe that the fluid is going to be going through, and that's what you're modeling. If it's heat transfer through a wall, what you just need to produce as the geometrical model is just the wall itself in its full dimension. Depends on the kind of analysis you're doing, whether it's one dimensional, whether it's two dimensional, whether it's three dimensional. Then the next thing to do is to mesh. Once you have that geometrical model, the next thing is to get another model that has of that geometrical model that is made up of small shapes, smaller elements that came together to form this entire domain. Now once you're done with meshing, the next thing is to get what you call a trial function, from which you determine what you call the interpolation polynomial. Trial function is more like usually a polynomial equation that is used to represent the shape, the small elements, the shape that you're talking about. Then after you've done that, the next thing is to determine what they call local solution. To determine local solution simply means to solve that governing equation for one element, and there are different methods that are used to do this. We'll talk about that subsequently. Then after that, you do same for all the elements, then you bring them together, what you call connectivity, to develop what you call a global matrix. That's a system of different simultaneous equations that represent, each of the equations may represent the behavior of an element. They are brought together. Then after that, you solve these global equations, which is usually in a matrix form. It's usually easy to solve. If you understand your matrix operation very well, you should be able to understand what it means to solve simultaneous equations that are in matrix forms. So we're quickly going to illustrate this with an example. Let's assume this is a system and it's subjected to heat at one end. I want to assume that the heat is going to flow from the left side to the right side. That's from where it's being heated to the other extreme, and it's going to flow in one direction and via conduction only. If that is the case, the next thing to do is to bring our governing equation. And this is our governing equation, for example. This is one-dimensional heat flow equation. When heat is going to flow in one dimension, one direction, and there's the heating source. And the next thing to do after this is to get your geometrical model. You mesh it. You mesh means you break this into small elements. Like this, for this case now, we want to say, oh, this heat is going to move in a straight line. So let's break this thing into small straight lines. And once you've done that, you've meshed. Then the next thing to do is to get what you call a trial function. I said earlier that trial functions are primarily polynomial equations. For this case, because it's a linear model, we can say, well, this equation will suffice. This equation will do yt is equal to a0 plus a1x. Some other person can say, no, I don't believe this heat will flow in a straight line. Let's add another term, and that person will say yt is equal to a0 plus a1x plus a2x squared. Whatever be the case, it's called a trial function. You want to use that function to describe the equation. Then after that, the next thing to do is to solve your elemental equation. And I said there are different methods to do this, to seek solution to an element. They have the Rees method that is very old. Then the variational method. The variational method has some limitations, and the primary limitation of the variational method is that for variational method you need to get what you call variational formulation, and variational formulation do not exist for different problems. Then after that, there's the weighted residual method, and there are many of its kind. We have the Galekin that is very popular. We have collocation method, we have least square method, you have subdomain, and you have pseudo spectra. So if you are using a finite element software, for example, the software would have embedded one of all these techniques in its program, that is used to seek elemental solution, then it does solve for all the different elements that the domain has been meshed into, and brings them back together in what you call connectivity to form one singular matrix. Then it solves it just the way you will solve simultaneous equations using matrices. We're quickly going to look at this weighted residual method and to illustrate it, just so you have an idea of what we are doing in finite element analysis. You will need a lot of several lectures, several examples to really be able to grasp the whole concept of finite element analysis, but this is just an introductory section, and I said it's just to present to us some of the basics in finite element analysis. So to illustrate that, we're going to see how weighted residual method, more specifically the Galekin method, is applied. And this formulation we see there, integral wi arrow within the domain a to b equal to 0, that is the standard formulation for Galekin procedure. The only question you need to answer to solve a differential equation using Galekin method is to determine what w is and what r is. A and b are just the integral domain, the boundary conditions from a to b. If it's a straight line from one end of the line to the other end of the line, that's just what boundary conditions is within an element. So we're going to look at an example quickly, but before then I want us to note that our trial function is key in finite element analysis. It's also something we need to know. Trial function is just a polynomial equation, usually a0 plus a1x plus a2x squared plus a3x cubed plus a4x raised to the power 4 plus a5x raised to the power 5 plus up to anx raised to the power n. But usually you truncate at any point. You can use only a0 plus ax1 plus a2x squared. Some other person can say, no, let's add the other two terms, a3x cubed plus a4x4. Some other person, so depends. There are really no restriction to this, but there are certain conditions that guides your selection of a trial function. But we're not going that into details. It's when you're studying elements and their trial function, suitable trial function or suitable interpolation function, that you begin to see that, oh yes, you are restricted. You cannot just truncate to make it too short an equation. There are limits to which you can do that. And summary is the function of the nodes. If it has two nodes, you're supposed to have at least two terms. If it has three nodes, you're supposed to have, the least you can have is 3 terms. If you have 4 nodes, the least you can have is 4 terms. Like this trial function that we have, yt is equal to a0 plus a1x plus a2x squared. It is 3 terms. But let's not be bothered yet about some of all these details I'm providing. We're going to walk through an example quickly, and once that is done, we see that this procedure, despite all these many stories I've told, it's easy to apply, and we should be able to apply this procedure at this level, and that's what we're going to illustrate with this example. So let's say we have a question, d2y ds squared minus 3x squared is equal to 28, and we have the boundary conditions, y0 is equal to 0 and y1 is equal to 0. What they're just saying here is when x is equal to 0, y is equal to 0, and when x is equal to 1, y is equal to 1. So knowing that, we want to solve this problem using this trial function. Yt is equal to a0 plus a1x plus a2x squared. This is the trial function, and this is what we're going to use to solve this problem using the Galekin procedure. So the first thing to do, before we begin, I want us to understand the basics in the Galekin formulation. The Galekin formulation just helps to address some of the things we have as a problem in this equation. Like we can see, we have 3 unknowns, a0, a1, a2. These are constant terms. In our trial function, once we can eliminate these terms, if these terms are no longer there, we have realistic numbers, and we are saying this trial function properly represents the governing equation that we have, or the problem at hand. Once we can eliminate all these terms and get real numbers to represent them, what we are doing, we have solved the equation, and we can just use our trial function to estimate any value of y when the value of x is given. So the first thing to do, if you are to do this, is to try to introduce the boundary conditions to eliminate some unknowns. Remember, we're given certain boundary conditions. We said when x is equal to 0, y is equal to 0. So we're going to start by introducing that. Y0 equal to 0. Just saying when x is equal to 0, y is equal to 0. So if we do that, put that into our trial function, we have that a0 plus a1x0 plus a2 times 0 raised to power 2, all is equal to 0. From this, if you simplify this, 0 times a1 is 0, 0 times a2 is 0, 0 squared times a2 is 0, so what is left is a0, and we have that a0 is equal to 0. But that's not enough. What else were we given? We're given another boundary condition, y1 is equal to 0. That is to say, when x is equal to 1, y is equal to 0. Put that into your trial function yt. What you have is a0 plus a1 times 1 plus a2 times 1 square is equal to 0, because when you're putting x is equal to 1, we also have y to be equal to 0. So by the time you put all these things through, everything will eliminate themselves. We already add a0 to be 0. It therefore means that we have something like this: 0 plus a1 times 1 plus a2 times 1 square is equal to 0. We can therefore say that a1 is equal to minus a2. So if we have this, what we have left is only a1, because we can put, is only either you put a1 in the place of a2, or you put a2 in the place of a1. So let's go by putting minus a2 in the place of a1, because we said a1 is equal to minus a2. So if we do that, calling back our trial function, y is equal to a0 plus a1x plus a2x squared, we have that y is equal to minus a2x. This is so because a0 is already 0, a1 is equal to minus a2, and then we have a2x squared. That's how we came about this last equation that we have here. So if we proceed from here, the next question we want to ask ourselves, how do we get a2? Because we've used all our boundary conditions. The next thing to do is to call, if we simplify further, you get something like this, but a2 is still there. The next thing to do is to call your Galekin formulation. With this, you can eliminate the a2 that is left. I don't want to go into details of how this equation is valid, how it came about, how it was derived. If there are subsequent lectures, we will take that. But we know that we are integrating 0 to 1. Remember, we said you integrate within the domain. For this case, the domain is between 0 and 1. Wi times r. Question we may ask ourselves, what is wi? We call that the weight function. Then what is r? We call that the residual function. So these two things are functions, but they are simple algebraic expressions, so you can bring them together, multiply them, expand your equation, you integrate, you equate to 0, then you look for an unknown. So to do that, we have to call back our initial equation. This is the equation we are working with. If this is our equation, then this is our interpolation function, which we just determined previously. This is our interpolation function. And if this is our interpolation function, we can easily get our weights. The weight, wi, I could be 1 weight, I could be 1, 2, 3, 4, 5, as many constants as you have left in the equation. For this case, we have just one constant left, that's a2. So whatever is multiplying that constant, we call it weight. So for this case, we have x squared minus x as the weight, because that is what is multiplying the constant a2. So that is our weight. X squared minus x is our weight. The next question we want to ask ourselves is, then what is the residual function? We're going to illustrate how that is done. Residual function, if you pick your equation, the initial equation, of course, we also have our trial function. If you make the initial equation to be equal to 0, that's take everything on the right hand side to the left hand side. For this case, you just bring 28 to the other side. You're likely going to have the 2y dx squared minus 3x squared minus 28. All this will be equal to 0. And if this is equal to 0, what we have is the whole of all this on the left hand side. If we equate it to 0, everything on the right hand, on the left hand side. So we can easily say that r is equal to the 2y dx squared minus 3x squared minus 28. The only thing is that the y now, you have to replace it with your trial function. So the y becomes the function that you are trying to solve. And for this case, we know that our trial function yt is equal to a2 into x squared minus x. So to fully get the value or the expression for your residual is to introduce, that's to bring in the value of yt back into the equation, and you simplify. We already have yt, we have the residual term, so if you do that, we have something like this. It becomes d2 dx squared a2 into x squared minus x. We have to differentiate this twice, minus 3x squared minus 28. And if you do this, by the time you differentiate, you simplify, you get our residual term, and that becomes r is equal to 2a2 minus 3x squared minus 28. Our weight, just to recap, is the terms that are multiplying the coefficients. If you have more than one unknown coefficient, maybe a2, a3, a4, our weight is just going to be 3. We're going to have 3 weight. For this case, because we have just one coefficient a2, we have one weight, x squared minus x. Residual becomes 2a2 minus 3x squared minus 28 weight. Once this is done, the next thing, you can go back to your Galekin formulation and solve out your problem to find the unknown. Remember, Galekin formulation, wi times r integrated within the bounds. For this case, our bounds or boundary condition are 0 and 1. We already have our weight, we have our r, so if you put all those things into an equation, this is what we are likely to get. We know our weight, x squared minus x. We know our r, 2a2 minus 3x squared minus 28. By the time all these things is put into the equation, what we have at the end of the day is something like this. So if you expand and you integrate, that is, use x squared minus x, that is in one bracket, to multiply 2a2 minus 3x squared minus 28. Once you've done that expansion and equate them to 0, you're going to have something like this. And once you've gotten something like this, the next thing to do is just to simplify. So we have our weight, we have our residual function, you have your Galekin procedure, you have what to simplify. By the time you simplify, you're likely going to get a2, a value for a2. a2 becomes 289 over 20. Once that is done, we know that we said that a1 is equal to minus a2. So from this, we can easily get a1. a1 is minus 289 over 20. And once you've done this, the problem is solved. This is our child function for the problem. We have a2 to be 289 over 20. We have a1 to be minus 289 over 20. We have a0 to be 0. Put everything back into the equation, you have this. The yt to be minus 289 over 20x plus 289 over 20x squared. And you can simplify further to get yt equal to 289 over 20 into x squared minus x. So once this is done, you are good to go. Sorry, before we proceed, we want to say that this trial function yt is equal to minus 289 over 20 into x squared minus x is the solution. This can give us an approximate value of y for any given value of x. So we're going to try to solve the same problem analytically. Of course, this problem has an analytical solution. So we're going to try to solve it analytically. So let's call back our problem. The 2y dx squared minus 3x squared is equal to 28. How do we solve it analytically? You just take everything to the right hand side. The 2y dx squared equal to 28 plus 3x squared. To solve this problem, we know you just integrate and you apply your boundary conditions. And if you do that, you're going to get y equal to 14x squared plus x4 over 4 minus 57 over 4x. This is the actual solution. And if you try to solve the same problem, maybe for values between 0 and 1, 0, 0.1, 0.2, 0.3, 0.45, 0.5, and to 1. And if you find solution, the answer to y for these given values of x, you will see that when you also seek the solution for y using the Galekin solution, the answers are similar. For example, when x is 0.5, the actual value for y is minus 3.60938. Then when you use the Galekin solution, you have minus 3.6125. They are very close, approximately equal. 3.6 minus 3.6. And if you look at the solution closely, you see that they are related. Well, This is that about Galekin procedure. You can try this out on your own. You try to work the same problem using another trial function, a0 plus a1x plus a2x squared plus a3x cubed. If you try to solve this, of course, the first thing to do, you put your boundary condition to eliminate as much constant as you can. For this case, we're able to eliminate a0 and a3, such that our trial function will be a1x 1 minus x squared plus a2x squared 1 minus x. Once this is done, the next thing to do is to know that these are two weights. You have two weights. I said weight is anything that is multiplying your constants. For this case, a1 and a2 are the constants. Then you have your residual function. Your residual function, which we can see here, is just the other part. Take everything to the left hand side and equate it to r, then bring in your trial function yt in the place of y. Then you simplify. When you simplify, you get r to be this. Then once that is done, you call your Galekin formulation. Your formula, always remember, the bounds is not always going to be between 0 and 1. We're using 0 and 1 here because this is the boundary conditions that we have when x is 0 and when y is 0. That's why when x is 0 and when x is equal to 1. That's why we're using that. Of course, we know that this is a boundary value problem. It could be an initial value problem where we have the initial conditions and the final conditions. So by the time you do this, you're going to have two equations using the different weights to multiply residual for the first one. Then you do same for the second one. By the time you simplify these two equations, you are likely going to get two simultaneous equations. And if you solve the simultaneous equation, you get two values, one for a1 and another value for a2. And if you take that back into your equation, you get your value for trial function. So with this, you can begin to find values of y for different values of x. So this is that about the Galekin procedure. Thank you very much. I really do hope that this thing is clear enough. It could be very useful for your exam, as you're likely going to solve a problem using a simple problem, using either the Galekin formulation especially in your exam. But if you're more familiar with the variational technique, it's also okay. But it's good you understand this procedure, and this is the basis of finite element analysis. Every other thing that is done, this same thing I just did here, is done for